The quantum frontier, a new view of the universe. In the early 20th century, physicists stood on the edge of an extraordinary scientific shift. Classical physics, with its tidy rules governing motion, gravity, and electromagnetism, had long provided a reliable framework for understanding the natural world. But as researchers delved into the subatomic scale, they encountered behaviors that defied everything those elegant laws had predicted. The initial seeds of this theory were planted in the late 1800s during investigations into blackbody radiation. Scientists were attempting to determine why heated objects, like metal rods, emit energy in specific patterns. According to classical physics, such objects should release an infinite amount of energy across all wavelengths when extremely hot. But real-world measurements painted a different picture. Radiation appeared only at specific wavelengths, and the emitted energy was limited. This contradiction became known as the ultraviolet catastrophe, a dilemma traditional physics couldn't resolve. Then, in 1900, German scientist Max Planck proposed a bold hypothesis. Instead of energy being released in a continuous stream, it was emitted in individual, fixed units, or quanta. This marked the first significant rupture in classical physics. Planck's revolutionary insight introduced the idea of quantization, that energy at its most fundamental level comes in set amounts. Although Planck's discovery resolved the blackbody radiation issue, many considered it a mathematical workaround rather than a shift in physical understanding. That changed in 1905, when Albert Einstein took Planck's idea further. While analyzing the photoelectric effect, Einstein argued that light itself wasn't just a wave, as previously thought. It also exhibited particle-like properties. He theorized that light consisted of discrete energy packets, which he called photons. When photons struck a material, they could transfer energy to electrons, causing those electrons to be ejected from the surface. This groundbreaking idea demonstrated that light could act as both a wave and a particle, a phenomenon later known as wave-particle duality. Einstein's explanation earned him the 1921 Nobel Prize in Physics and helped lay the foundation for quantum theory. Quantum theory advanced further in the mid-1920s with major contributions from Werner Heisenberg, Erwin Schrödinger, and Paul Dirac. In 1925, Heisenberg developed matrix mechanics, a mathematical method for describing particles using measurable values like position and momentum. Although groundbreaking, this method offered little visual intuition. Although such questions still inspire debate and research, one fact remains indisputable. Quantum mechanics has profoundly transformed our understanding of the cosmos. It's more than a scientific theory, it's a new lens through which we see the fabric of reality. Precision meets limits. Understanding the uncertainty principle. This experience mirrors a key concept from quantum theory, Heisenberg's uncertainty principle. Just like in photography, where focusing on one detail sacrifices clarity elsewhere, you can't precisely determine both the position and momentum of a quantum particle like an electron at the same time. No matter how advanced our tools become, this is a fundamental truth of the quantum world. In this new framework, particles weren't seen as hard, tiny balls, but as probability waves, clouds of possible positions and energies. Depending on how they were observed, particles behaved like either waves or solid particles, a jarring realization that deeply shook classical physics. Heisenberg, while studying how electrons interacted with light, noticed something unusual. The more precisely a particle's location was known, the less certain its momentum became, and vice versa. This wasn't just a measurement error, it was a fundamental aspect of nature. He concluded that some pairs of physical traits, like position and momentum, had a built-in limit to how precisely they could be known together. This insight became the uncertainty principle. Mathematically, Heisenberg's equation showed that the product of the uncertainty in position and the uncertainty in momentum could never drop below a certain value. This meant that knowing one with absolute accuracy made the other inherently fuzzy. At first, this may seem like a problem with instruments. But Heisenberg's point was deeper. The universe itself doesn't allow exact knowledge of both traits at once. This wasn't about flawed tools. It was about the very nature of quantum reality. Before this discovery, classical physics was rooted in determinism, the belief that if you knew everything about a system in the present, you could predict its future. Whether it was a planet or a baseball, every object's path could be calculated precisely. But quantum theory disrupted this certainty. Quantum particles didn't follow a single trajectory. They existed in a haze of possibilities. The uncertainty principle also sparked deep philosophical debates. Could we ever fully know a system, its position, energy, and velocity? According to Heisenberg, the answer was a definite no. Measurement itself changed the system being observed. In classical science, we assumed observing something didn't affect it. But quantum theory revealed that observation alters reality. When we measure a particle, we collapse its wave-like potential into one outcome. This interpretation, developed by Bohr and Heisenberg, became known as the Copenhagen interpretation. In this view, quantum reality isn't fixed until it's observed. Although the uncertainty principle may seem abstract, it has practical consequences. One real-world result is quantum tunneling, where particles pass through barriers they shouldn't be able to cross based on classical physics. This is what enables key technologies like semiconductors and MRI machines. While the quantum world often feels strange and alien, it underpins everything we use and experience. The uncertainty principle isn't just a quirky idea, it's a cornerstone of modern physics, defining the very limits of what can be known. Unveiling the electron. A milestone in modern physics. In the closing years of the 19th century, scientists were on the verge of a groundbreaking breakthrough in the realm of physics, the discovery of the electron. Before this revelation, the internal composition of atoms was poorly understood, and many believed atoms to be the smallest, indivisible components of matter. This belief originated from ancient Greek thinkers, notably Democritus, who introduced the term atom from the Greek word atomos, meaning indivisible. However, as experimental techniques became more refined, researchers began uncovering evidence that suggested atoms were not as simple as once believed. Among the most crucial developments in this unraveling was the identification of the electron, a discovery that would forever transform our grasp of atomic structure. Experiments throughout the late 19th century began revealing that these rays could be influenced by magnetic and electric fields, suggesting they behaved like particles. Still, the scientific community was split. Some continued to argue that cathode rays were a novel form of electromagnetic wave, while others believed they were material particles. The puzzle was eventually solved by British physicist J.J. Thomson in 1897. Working at the Cavendish Laboratory in Cambridge, Thomson conducted a series of precise experiments aimed at understanding the properties of cathode rays. By constructing a specially designed cathode ray tube that allowed the application of both electric and magnetic fields, he was able to measure how the rays responded to these forces. This setup enabled Thomson to fine-tune the strengths of the electric and magnetic fields until the rays' deflection was neutralized. With this balance, he calculated the charge-to-mass ratio of the particles within the rays. The outcome was astonishing. These particles were approximately 1,800 times lighter than the hydrogen atom, the smallest known atom at the time. Thomson deduced that cathode rays were made up of extremely small, negatively charged particles that were part of all atoms. This finding upended the long-standing belief that atoms were indivisible. Not only had he demonstrated that atoms contain smaller components, but he had also discovered the first known subatomic particle, which he named the electron. To make sense of this groundbreaking observation, Thomson introduced a new atomic model. He suggested that if atoms had negatively charged electrons, there must be some form of positive charge present to maintain electrical neutrality. This idea led to his famous plum pudding model, where the atom was envisioned as a positively charged sphere embedded with negatively charged electrons, much like raisins in a pudding. Inspired by Thomson's discovery, other scientists delved deeper into atomic research. Ernest Rutherford later identified the atomic nucleus, and Niels Bohr developed a quantum-based model of the atom. Moreover, Thomson's findings laid the foundation for an entirely new field, electronics. The understanding of electron behavior led to the invention of semiconductors, transistors, and ultimately, modern computers and digital technology. The discovery of the electron signaled the dawn of quantum physics and set the stage for many of the 20th and 21st centuries' most important scientific achievements. Through his unwavering pursuit of the unknown, J.J. Thomson not only found a new particle, he reshaped humanity's understanding of the very building blocks of matter. Rewriting the universe. Einstein and the theory of relativity. At the beginning of the 20th century, science stood at a crossroads. Classical physics, rooted in the laws laid down by Isaac Newton, had dominated for centuries, governing ideas about motion, gravity, and the structure of the cosmos. Yet strange phenomena were beginning to emerge, which Newtonian physics couldn't explain. Born in 1879, Einstein was a bold thinker who imagined physical principles not just through mathematics, but through visualized mental experiments. Intrigued by the behavior of light, he discarded the ether concept and proposed something revolutionary. What if space and time weren't fixed, but could change depending on motion and gravity? This idea culminated in Einstein's 1905 paper on the electrodynamics of moving bodies, where he introduced the theory of special relativity. At its core were two profound postulates. The laws of physics are identical for all observers, regardless of their uniform motion. The speed of light is the same for all observers, no matter their relative velocity. This new interpretation of gravity transformed physics. It explained phenomena Newton's theory couldn't, such as the orbit of Mercury or the bending of starlight near the Sun, which was confirmed during the 1919 solar eclipse by Arthur Eddington. The impact of relativity was immense. It formed a foundation for modern physics, influencing everything from black hole research to cosmology. Even GPS systems depend on Einstein's theories to correct for time dilation caused by satellites orbiting Earth. Light, electrons, and the birth of quantum theory. The interaction between light and matter, known as the photoelectric phenomenon, represents a critical breakthrough in the evolution of quantum science. It signaled a turning point in humankind's quest to decipher the baffling and often paradoxical realm of elementary particles. During the early decades of the 20th century, scientists found themselves facing a series of puzzles, phenomena that defied the well-established principles of classical mechanics. Among these was the curious way in which light, when striking metal surfaces, would liberate electrons. This effect contradicted the prevailing ideas physicists held about the nature of light. Then came Albert Einstein, whose revolutionary perspective on the photoelectric phenomenon not only unraveled this perplexing behavior, but also became a cornerstone of the emerging quantum framework. To appreciate how pivotal this discovery was, we must step back and examine the scientific context of that period. In the 1800s, the dominant belief was that light behaved solely as a wave. This understanding was eloquently reinforced by James Clerk Maxwell, whose mathematical descriptions portrayed light as an electromagnetic disturbance, fluctuating electric and magnetic fields rippling through the void. This wave-based perspective successfully accounted for a host of optical effects, including diffraction and the spectrum of colors seen in rainbows. However, anomalies arose when light interacted with metallic objects. Researchers found that illuminating a metal with light of specific frequencies caused the metal to emit electrons, a response termed the photoelectric effect. This result posed a significant challenge to classical physics. If light were purely a wave, why would frequency matter more than intensity in triggering the emission of electrons? This was the problem Einstein tackled in 1905. In a groundbreaking scientific paper, he introduced a daring hypothesis. Light might not just be a wave. It could also act as a stream of discrete energy units. These units, initially called quanta and later termed photons, contained energy directly linked to their frequency. Einstein theorized that when light hits a metal, it's these individual photons, not the collective wave, that transfer energy to electrons. If a photon carries enough energy, i.e., its frequency is above the threshold, it can eject an electron from the metal's surface. Conversely, if the photon's energy falls short of the threshold, it cannot dislodge an electron, no matter how intense or bright the light is. In classical wave theory, intensity is related to the wave's height or amplitude. Greater intensity should mean more energy and hence more electrons being released. But Einstein's particle-based model flipped this concept. In his view, frequency, not brightness, determines whether electron emission occurs. So even a powerful low-frequency light beam cannot free electrons if each photon lacks sufficient energy. Only high-frequency light, such as ultraviolet, possesses photons energetic enough to liberate electrons. This insight paved the way for the rise of quantum mechanics, a field that governs the behavior of the tiniest constituents of the universe. Einstein's findings revealed a profound truth: the realms of energy, light, and matter are deeply interconnected. Moreover, light can exhibit both particle-like and wave-like traits depending on how it is observed, a principle now known as wave-particle duality. While Einstein's explanation of the photoelectric effect was revolutionary, it initially faced skepticism. The idea that light could function as both a wave and a particle defied centuries of established scientific belief. Still, the accumulating experimental evidence was irrefutable. Numerous tests validated Einstein's predictions, and in 1921, he received the Nobel Prize in Physics, not for relativity, but for his insight into the photoelectric effect. Beyond theoretical implications, the photoelectric effect also brought forth practical innovations. The principles behind it are used in solar panels, which convert sunlight into electricity, as well as in light-sensitive devices like photodetectors and sensors. All of these technologies rely on the principles Einstein helped to uncover. Far from being an obscure scientific curiosity, the photoelectric effect was a crucial clue in the broader effort to understand how light, energy, and matter function at the most fundamental level. Einstein's interpretation stands as one of the most influential contributions in the history of modern physics. It demonstrated that light is dual-natured and set the stage for the quantum revolution that followed. Ultimately, the photoelectric phenomenon offered a glimpse into the surreal world of quantum behavior, a domain where energy appears in bursts, particles behave like waves, and space and time lose their rigidity. And it all began with a deceptively simple question about how light interacts with metal, an inquiry that continues to shape our understanding of the cosmos through the lens of quantum mechanics. Unveiling the science of heat, the rise of thermodynamics. As the modern world began to change, scientists observed intriguing patterns involving heat, energy, and mechanical work. During the Industrial Revolution, engines that ran on fuel became the driving force behind ships and factories. However, while engineers excelled at constructing these machines, they couldn't quite understand why some engines operated more efficiently than others. This uncertainty initiated a new era of scientific exploration, the birth of thermodynamics. This intellectual journey commenced in the early 1800s with Sadi Carnot, a French engineer who is often recognized as the founding figure of thermodynamics. Carnot sought to enhance the efficiency of steam engines, which served as the industrial age's core technology. He imagined heat as a peculiar fluid capable of flowing between bodies, carrying energy in its path. In 1824, he published a modest book in which he introduced the concept of the perfect engine cycle, now known as the Carnot cycle. The first law of thermodynamics asserts that energy cannot be created or destroyed, it only changes form. Known as the principle of energy conservation, this concept was reinforced by James Joule during the 1840s. Joule executed a brilliant and straightforward experiment. He attached weights to a paddle while submerged in water. As the weights fell, they rotated the paddle, stirring the water and raising its temperature. This experiment showed that the mechanical energy from the falling weights was converting into thermal energy. In the late 1800s, scientists delved further and established the third law of thermodynamics. Proposed by Walther Nernst, this law states that as the temperature of a system nears absolute 00 Kelvin or minus 273.15 degrees Celsius, its entropy approaches a minimum. At this ultimate cold point, a system would be in perfect order, with zero random motion among its particles. Although absolute zero is theoretically defined, it's practically unreachable. The closer one gets, the harder it is to eliminate the last traces of energy. This third law deepened our understanding of materials at extremely low temperatures and paved the way for studying superconductivity and exotic quantum states. These laws of thermodynamics aren't just theoretical ideas, they are central to how we manage and understand energy. They explain why engines need fuel, how fridges stay cold, and how stars live and die. From chemical reactions to biological functions, thermodynamics is essential. From improving early steam engines to predicting the end of all energy-driven activity, thermodynamics remains a vital framework. It reveals how energy flows, powers life, and shapes the evolution of the universe itself. The journey into electromagnetism. From classroom curiosity to universal force, the tale of electromagnetism begins in the early 1800s with a simple yet revolutionary realization: electricity and magnetism are not isolated forces, but are in fact two sides of the same essential phenomenon. Although this concept may seem obvious to us now, it was a paradigm shift for the scientific community of the 19th century and completely transformed how we perceive the forces governing our physical reality. Among those intrigued by Ørsted's findings was Michael Faraday, a British scientist whose tireless work propelled the idea of electromagnetic interaction to new heights. Inspired by the possibility that electricity and magnetism were interrelated, Faraday devised experiments to push Ørsted's conclusion even further. Although Faraday revealed the workings of electromagnetic induction, he never developed a complete theory that unified electric and magnetic forces. That task fell to James Clerk Maxwell, a Scottish physicist whose work in the mid-1800s would consolidate the scattered discoveries of Ørsted, Faraday, and others into one unified system. The emergence of modern communication systems also stems from our grasp of electromagnetic theory. In the late 19th century, Heinrich Hertz provided experimental proof of radio waves, validating Maxwell's predictions. This set the stage for inventors like Guglielmo Marconi, who developed techniques to transmit signals wirelessly, leading to the creation of the radio. Since then, advances in radio waves, microwaves, and fiber optics have revolutionized global communication, enabling near-instant transmission of data over vast distances. Even breathtaking natural phenomena like the aurora's northern and southern lights arise due to electromagnetism. When solar-charged particles hit Earth's magnetic field, they spiral along magnetic lines and interact with atmospheric gases, causing glowing curtains of red, green, and blue light to dance across the sky. Electromagnetism is more than a scientific branch. It is one of the foundational forces of physics. From Ørsted's classroom experiment to Maxwell's theoretical brilliance, the study of electromagnetism has reshaped human civilization. Its principles are embedded in everyday technologies, from lighting and electronics to satellites and smartphones, and even in our exploration of the cosmos. Today, we continue to expand on this legacy. The field of quantum electrodynamics (QED), which merges electromagnetism with quantum theory, has opened up even deeper understandings of how particles interact. As we venture further into the unknown, one thing is certain: electromagnetism, a fundamental force of the universe, will remain a driving force behind the next wave of scientific and technological breakthroughs. The legacy of Newton's motion and gravity framework. Throughout the chronicles of physics, few breakthroughs have had as lasting an influence as Isaac Newton's establishment of the motion laws and the principle of universal gravitation. These transformative revelations not only redefined humanity's comprehension of the natural world, but also built the cornerstone of classical physics, a framework that directed scientific progress for over 3 centuries. Newton's contributions are still integral to how we understand phenomena ranging from planetary orbits to rocket propulsion. The narrative of Newton's work is often linked to the iconic scene of him under an apple tree, witnessing a fruit drop to the earth. Though likely simplified over time, this tale captures the heart of Newton's curiosity. Born in 1642, Isaac Newton was a scientist, mathematician, and astronomer who sought to unravel the fundamental workings behind motion and interactions in the cosmos. During that era, there was no clear grasp of the dynamics governing objects, either on Earth or in the celestial realm. As legend tells it, one day Newton saw an apple fall vertically to the ground, prompting him to question why it didn't travel sideways or in a random direction. This simple moment of wonder sparked a series of thoughts that culminated in one of science's most influential milestones. Newton deduced that the same force drawing the apple earthward also governed the moon's path around our planet. This epiphany laid the groundwork for his theory of gravitation. Before Newton, thinkers had developed ideas about motion, but a cohesive mathematical explanation was missing. In 1687, Newton introduced his laws of motion in his monumental text Philosophiae Naturalis Principia Mathematica. These laws formed a unified framework describing how objects behave when subjected to various forces, principles that remain central to classical physics today. His first law asserts that a stationary object will remain unmoved, and a moving object will keep traveling in a straight line at constant velocity unless a net external force disrupts it. This notion of inertia was groundbreaking, contradicting Aristotle's view that continuous motion required ongoing force. Newton revealed that in the absence of influences like friction or gravity, motion would persist indefinitely. For instance, imagine sliding a hockey puck across a perfectly frictionless ice surface. It would keep gliding endlessly in a straight line unless acted upon. Newton's second law details how a force affects an object's motion, stating that force equals mass times acceleration. This formula connects the dots between force, mass, and movement, forming the mathematical basis of dynamics. It explains why, when equal force is applied to a shopping cart and a car, the cart accelerates more quickly, it's much lighter. The third law states that every action has an equal and opposite reaction. This rule applies to all forms of interaction, whether direct or remote. If you press against a wall, the wall pushes back with an equal force. Even though you may not move the wall, the reactive force is still there, matching your push in magnitude, but opposite in direction. Together, these 3 laws form the core of Newtonian physics, allowing scientists to precisely model and forecast how objects behave under a range of conditions, be it a rolling ball or a planet in orbit. While Newton's motion laws offered a strong foundation, his theory of gravitation fundamentally altered how we perceive the universe. Newton proposed that all objects attract one another with a force that weakens as the square of the distance between them increases. What set Newton's insight apart was its universal scope. It didn't just apply to falling objects on Earth, but also to celestial bodies like moons and stars. In connecting earthly motion to cosmic phenomena, Newton unified terrestrial and astronomical physics under one principle. The same force pulling an apple downward also kept planets in their orbits, a profound realization that brought harmony to the heavens and earth alike. Newton's theoretical framework reshaped our understanding of planetary movement, projectile paths, tidal behavior, and more. It also laid the scientific groundwork that thinkers like Einstein and the pioneers of quantum mechanics would later build upon. Newton's ideas had practical value. 2. Understanding forces and motion enabled innovations such as spaceflight and satellite technology. When humans first walked on the moon in 1969, it was Newton's laws that guided the calculations and engineering. Modern rockets, spacecraft, and orbital mechanics are all rooted in these foundational concepts. Despite their monumental success, Newton's laws were not the final chapter. In the early 20th century, Einstein's theory of relativity expanded upon Newton's model, especially in extreme conditions like the intense gravity near black holes or objects moving at light-like speeds. Nonetheless, Newton's principles remain incredibly effective in real-world scenarios and are widely used in engineering and daily physics. Ultimately, Newton's contributions, his three motion laws, and his theory of universal gravitation represent one of the most extraordinary achievements in scientific history. By synthesizing prior knowledge with original thought, he illuminated the workings of the physical world and crafted a legacy that continues to steer modern science. From apples to astronauts, Newton's insights remain a guiding beacon in physics and engineering. Rutherford's atom revelation, the gold foil breakthrough. In the early 1900s, the quest to decipher atomic structure was a driving force in physics. At the time, the most accepted model was J.J. Thomson's plum pudding theory, proposed after his 1897 discovery of the electron. According to this concept, atoms consisted of a positively charged pudding with negatively charged electrons scattered within, similar to raisins in dough. However, this model faced a major challenge through one of the most significant experiments in scientific history, Ernest Rutherford's gold foil experiment. At the dawn of the 20th century, scientists agreed that atoms contained both positive and negative elements, but the arrangement of these components remained unclear. Thomson's idea, though popular, lacked solid evidence and left many questions unresolved. Was the positive charge uniformly distributed? Where were electrons located? What ensured atomic stability? In 1909, New Zealand-born physicist Ernest Rutherford, working at the University of Manchester, set out to explore these mysteries. Driven by a deep curiosity about atomic forces, Rutherford, alongside his assistants Hans Geiger and Ernest Marsden, designed a groundbreaking experiment that would forever reshape atomic theory. Their setup involved projecting alpha particles, positively charged particles, composed of 2 protons and 2 neutrons, at an extremely thin sheet of gold foil. Alpha particles were selected due to their substantial mass and energy, which allowed them to penetrate matter easily, a key aspect for testing atomic models. If Thomson's plum pudding theory were accurate, these alpha particles should have passed through the foil with only slight deviations, as the positive charge was thought to be diffusely spread throughout the atom. The team used a special detection screen coated with zinc sulfide to monitor particle behavior. When struck by an alpha particle, the screen would emit a small flash of light, revealing its trajectory. To their astonishment, while most particles passed through the foil as expected, a small but significant number were deflected at sharp angles. Some even bounced back toward the source. Rutherford was so surprised that he later likened the result to firing a large shell at tissue paper and having it ricochet back. Such dramatic deflections could not be explained by the existing model. Clearly, there was a concentrated and powerful region within the atom capable of repelling incoming alpha particles. Rutherford concluded that this region, the nucleus, must contain nearly all of the atom's mass and carry a strong positive charge. Rather than a spread-out positive field, atoms contained a tiny, dense core, the nucleus, with electrons moving around it. This discovery transformed the vision of the atom from a diffuse pudding to a more organized structure, somewhat akin to a solar system where electrons orbit a central sun-like nucleus. This nuclear model aligned with experimental observations and paved the way for the later planetary model, which introduced specific electron orbits as proposed by Niels Bohr. Rutherford's work was not only critical for atomic theory, but also laid the foundation for nuclear physics. In 1917, Rutherford became the first person to deliberately split an atom, identifying the proton as a key building block of atomic nuclei. His findings also shifted how we perceive matter itself. The notion that atoms are mostly empty space was revolutionary. It meant that the solidness we feel is due to electromagnetic forces, not densely packed matter. This insight would eventually influence the development of quantum theory, as scientists examined the subtler forces governing subatomic particles. Rutherford's experiment, simple in design yet profound in consequence, challenged prevailing assumptions and unveiled one of the universe's deepest secrets. His pioneering work didn't just refine existing atomic models, it fundamentally altered the trajectory of modern physics. Today, the gold foil experiment is hailed not only for its discoveries, but for exemplifying how a thoughtfully crafted experiment can topple long-held beliefs and usher in a new scientific era. Rutherford's legacy embodies the essence of scientific pursuit, a seemingly modest test that answered monumental questions and continues to guide our understanding of matter at its most fundamental level.